Hello everyone, and welcome to the next virtual seminar. This is Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are eager to learn about our this webinar seminar series, that is structural rehabilitation and strengthening using FRP composites. Our full day virtual seminar is from 10 a.m. to 5 p.m. Stay tuned in. We have 7 total presentations. For continuing education credit, attendance for the entire duration of today's live virtual seminar will earn you a certificate of completion of 6 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 6 learning units. Please take note of our disclaimer on the screen for all the presentation in today's virtual seminar. This is our program. We are going to start with our first presentation. Our presentation title is Introduction to ACI Code 440.13, Strengthening Structural Concrete with Fiber Reinforced Polymer Systems. And our first speaker is, I'm happy to introduce him. He is Dr. Kent Harries. He is a professor of structural engineering and mechanics at the University of Pittsburgh. He was the chair of ACI Committee 440S with promulgated ACI Code 440.13. He has been an active ACI member for more than 30 years, to be specific, maybe 33 years, and he is also a fellow of ACI, ASCE, and IIFC. I welcome him.
All right. Okay. Thanks, Aparna. There's my disclaimer. Those of you who know me know that there will be opinions in this particular webinar, and they are mine, and they don't reflect particularly necessarily my fellow committee members. My presentation, I'm going to speak, I'm going to introduce the brand new ACI Code 440.13. In fact, it is so new, it still doesn't quite exist, although it will by the time we all meet in Philadelphia, I've been assured. And so this little picture on the screen is something I have mocked up. It may not be exactly what things look like. The relevance to this is the first code language document addressing the structural repair of concrete with FRP materials. And as Aparna mentioned, I chaired the committee 440S that prepared this. Very, very briefly, the objectives of this particular presentation are really just to introduce the attendees to the scope and probably much more importantly, the current limitations of the new 440.13 document, and to place this into perspective. As to why the document was put together, and maybe provide a little bit of insight into the reason or the reasons why it is the way it is in its first iteration. So before I start, I want to talk a little bit about codes and standards very briefly for innovative materials, for new materials, for FRP. And don't get me wrong, FRP still is a relatively new material. And so I want to paraphrase Toby Mottram, who wrote, to be able to write a consensus standard, the stakeholder community requires mature practice from which lessons can be learned. To reach this level of practice, standards are required in order to overcome reluctance and cost barriers. And so we end up with this kind of catch-22, is that we need standards to move the industry forward, but the industry needs to be moving forward before we can have standards. And so that places the new 440.13 document in what I call a version 0 type of document. It has some limitations placed on its scope, more so than its background material, as I'll discuss a little bit, and future revisions are there to address these. The concept of getting a version 0 document out there is it allows people to see where we're headed. It provides a lingua franca, and it provides a foundation on which we can build better documents into the future. So I would like you to kind of think throughout this presentation with that sort of background in mind. I'd like to present the development of the 440.13 document and sort of its history. ACI 440 as a committee, FRP reinforcement was formed, I believe it was in 1992, and produced the first state-of-the-art report back in 1996. So we've been doing this for about 30 years now. With regard to FRP strengthening systems, 2002 saw the very first guide document. 440.2 is an emerging technology document. That document was revised in 2008, 2017, and again very recently in 2023, and remains a guide to the design and construction of FRP strengthening systems. From the 2023 version, we have then developed the 440.13, the 2024 code document, and it has some limitations. It doesn't repeat, excuse me, everything that's in 440.2, but builds upon it. Going forward, both of these documents will continue to be living documents. The code will certainly be revised going forward, and the 0.2 guide will continue to be revised and really be a venue for vetting newer materials before they find their way up into the code. So that's where we stand. All of these, and particularly the code itself, are enabled by specifications, particularly material specifications. I'm going to refer to a few of these today as well. And so these are the 440 specifications, 440.8 and 0.12. I'll refer to those a little bit later, and a large suite of ASTM standards that are enabled through Committee D30. And we need those in order to also have this design code. So a little bit of background. 440.13 is a mandatory language standard for FRP-based repair and rehabilitation, and is intended to live in the context of ACI Code 562, the Repair of Concrete Structures Code, which itself is then adopted by reference in the International Existing Building Code. Earlier versions of 562 weren't really able to specify FRP-based repairs, which of course are a very, maybe not a common, but a very important alternative repair technique, because there was no mandatory language standard. And so 440.13 was commissioned, as it were, to fill that gap. The new language in 562, this may change very slightly, but with respect to FRP, is simply those two lines on the bottom of the screen. Fiber reinforced polymer systems for repair and strengthening of concrete members and structures shall be designed in accordance with ACI Code 440.13. And there should be a period at the end of that, full stop. There will be no other material related. Everything will come to 440.13. I do want to comment very briefly on the title, because we actually did have some discussion about this. The 562 code is repair and rehabilitation of existing concrete structures. We intentionally entitled the 440.13 strengthening, because that's what the FRP applications do. They strengthen from existing conditions. And therefore, this doesn't necessarily imply restoring original conditions. It doesn't necessarily imply going beyond initial conditions. It may simply be restoring or strengthening an existing structure to meet adequate or serviceability type conditions that we may impose upon it. And so that was a difference between the two documents that was important. All right, I'm going to try to keep this relatively quick. The organization of 440.13 kind of looks a lot like most other codes that we see. We have a few chapters of boilerplate up at the front, notations and reference standards. The design chapters 4 through 9 go through the various actions, and I'm going to touch on each of these, highlight each of these as we go on. And then chapters 10 and 11 address special considerations for FRP, where issues with fire resistance are a little bit different for FRP systems, and of course field inspection may be a little bit different and a little bit less known to some users, and so we have these kind of special consideration chapters. I tell my students, you pick up a code document, the very first thing you need to do is look at the scope. What are we talking about? And I'm going to focus in this presentation a little bit more on what 440.13 doesn't discuss, its limitations, and maybe how it's going to go forward from there, because I think understanding limitations is likely more important. I suspect that most people on this seminar have a passing familiarity with the 440.2 guide. So first of all, the code does not apply to the strengthening of masonry structures. That is still addressed as a guide for 40.7 and addresses only seismic design category, structures in seismic design category A, or members in other seismic design categories that are not designated as part of the seismic force resisting system. So we have not included the seismic strengthening that is presently in the guide for 40.23 in this particular document. And some of that was based on the relatively short fuse for getting the 440.13 document out. Both of these issues, I hope, will be addressed in the next version of .13. Certainly the seismic will be, and I think that particularly extending this to some masonry structures may be as well. So let me talk about what the code addresses. The 440.13 talks about externally bonded systems. These come in two primary flavors: true externally bonded, where we're applying an FRP material to the outside of the concrete, to the surface of the concrete. Also, the near surface mounted application, where we cut slots into the existing concrete, inserting bars. The near surface mounted application, we always tend to show it, as I've shown it here on the right, replacing tension reinforcement, but it sees a lot of application actually on the tops of slabs because it embeds the additional reinforcement, the strengthening reinforcement, getting it away from that wearing surface. So there's a nice application there. I want to talk a little bit about the materials that we talk about for the strengthening systems, and we do talk about systems. We don't talk about just carbon fiber or glass fiber. We're talking about the carbon fiber, the glass fiber, along with the saturating resin, along with the adhesive, and so forth. And so if we want to run a typical design standard, we need material specifications to attach this standard to. In the classic analogy, the standard is the cart and the material specifications are the horse. When we're dealing with FRP materials, we're dealing with proprietary materials and sometimes new materials, evolving materials. And so our material specifications all look a little bit different. In my analogy here, they all have a similarity, they all have a beak, but they all come in different flavors. And so that becomes a challenge for specifying material systems. And so now I want to talk a little bit about how we address that. So the material systems addressed in 440.13 are addressed in Chapter 4, externally bonded on the left, near surface mounted on the right. And we talk about wet laid up carbon, which has an existing specification for 440.12, wet laid up glass, 440.8, and pre-cured carbon strips. These are the pre-cured materials that are then epoxy bonded to the surface of the concrete. And there's interestingly no existing specification for those. So that's a bit of a problem, which I'll come to in just a moment. On the near surface mounted side, we can talk about pultruded CFRP bars that are covered by ACI spec 440.6 and pultruded glass fiber bars, which are covered by ASTM D7957. Is the current specification for those. And of course, these pre-cured strips are also used on the NSM side, where we put a saw cut in and insert the strips vertically, as we've shown there on the right. So we have a little bit of an issue. We have specifications for most of the systems, but not for pre-cured CFRP. And that is important because that's a system that's quite commonly used. We did it, and so these are our different material specifications. And when we come to pre-cured CFRP, we have a little bit of a problem, and maybe are we putting the cart, the design specification, in front of the horse? We address this by essentially providing a mini specification within Chapter 4 for these pre-cured systems. We define minimum strength requirements, we define minimum modulus requirements, and requirements for the bonding adhesive that's used. And so this is now covered in Chapter 4 of the .13 document in order to address this lack of existing specification. And so we have these materials. Chapter 4 has been intentionally drafted in a way that we can also plug in new material systems relatively easily as they evolve, as they become viable. An example could be, now I appreciate that it's not a polymer, so we'd have to think about the title, but a lot of this document would be well suited to textile reinforced mortar applications potentially. And so we can look to that in the future. And again, there are those opinions that come. Okay, moving on to chapter 5 and essentially general requirements for design. Again, looking at externally bonded and near surface mounted. When we talk about externally bonded systems, we have two flavors of systems. We have systems that are bond critical, where the bond to concrete defines the performance of the system. And secondly, then we have contact critical, which really the typical example is confining let's say a round concrete column and lapping the FRP to itself. And so now the bond is FRP to FRP, and it is not absolutely critical that the bond to concrete be maintained. We have minimum requirements for substrate, concrete substrate that need to be met, and degraded substrates need to be brought up to these standards. And then we have surface preparation requirements for bond critical, which cite existing ASTM specifications, and contact critical, which are relaxed a little bit. Near surface mounted applications, one would argue a little bit more relaxed. We don't have a surface preparation requirement for these, but we do have requirements for grooves, which I'll come to in a moment. A key issue that when we're dealing with FRP materials, because they do behave a little bit differently, they are external applications, is then what load factors, what factored load cases do we need to address? And there are two special load cases that need to be addressed. And these are being addressed in this document because we needed something that existed by reference to Code 562, the 2021 version of that, and the two clauses. And really the point of each of these clauses is there in the red on the right. The first is for under normal operating conditions, we need to have a residual capacity of the existing concrete without the FRP in the event that the FRP is damaged. And in the second instance, we need to maintain sufficient strength due to a fire event. FRP is externally bonded FRP is essentially ineffectual during a fire. And so we have these two load cases. It is very difficult to separate load factors from design because these are critical limitations often to these kind of systems. And so in order to be perfectly clear, we have inserted an appendix into the 440.13 document that specifies these load factors. And we felt as a committee that this was absolutely important to have these together with the document. And so these are the factors that many of you are likely familiar with. And again, the top, when we talk about residual capacity of the unstrengthened element, and excuse me, the fire capacity in the event of a fire where the FRP is no longer contributing. I'm going to briefly go through some of the other chapters and just some of the highlights, looking at other limitations. I am assuming that many of you in this or watching this webinar are probably quite familiar with the 440.2 document, and so I'm not going to spend a lot of time on these, but we have things that should be recognizable. Of course, the so-called C sub E factors, the environmental exposure factors, which are applied to stress and strain, from which modulus is then obtained, and these are tabulated. There is a lot of effort going on within 440 right now to reconsider these factors, and so when they're put in a nice tabulated form, we're going to be able to update these into the future. There are maximum sustained loads, really addressing creep and fatigue issues. Maximum service temperature, again, the glass transition temperature minus 27 degrees Fahrenheit, which may limit FRP applications in some extreme situations. And then durability requirements for an FRP system. Most are a little bit more prescriptive here, but in particular, the ones I've highlighted here, making sure that the FRP doesn't seal the concrete system. We need to make sure that it can breathe and that we can allow moisture to escape from the existing structure. issues potentially associated with galvanic corrosion, carbon in electrical contact with metal can result in galvanic corrosion, or of steel, excuse me, can result in galvanic corrosion of the steel in certain conditions. And we also address the potential need, excuse me, for protective coatings as well. Moving on. The following chapters then really address, we have flexure, we have shear, we have axial force, all of those things that we're all used to designing for. Flexural design is covered by chapter 7, is a bond critical application, and we look at a limit states type approach where we have listed there the 6 limits that we might think about in a flexural application, from the crushing of the concrete all the way down to the debonding of the FRP and everything in between, and we need to satisfy each of those limit states. And this is essentially the same as what was presented in 440.2. Design is based on strain compatibility that we should all be familiar with as concrete designers. This image looks like something I teach to my first year concrete students. We use strain compatibility with no slip. We address the same types of stress strain relationships for steel and concrete. FRP is linear elastic. Traditional typical limits on steel and concrete stresses under service loads, and similarly FRP. I suppose the big difference in the strain compatibility is recognizing that the FRP is installed into the system when there's already existing strains on the existing steel and concrete, and so we do need to address this. And ultimately, the flexural applications typically are going to be governed by debonding strains of the FRP are going to limit our applications. And so that's a case that we need to make sure that we capture well. But there's no difference in the design philosophy when we're repairing concrete for flexure. Lots of nice details, just like with development length for steel. We need to taper out, we need to provide extensions beyond where material is needed. And so we have details for terminations, we have details for NSM applications, which include groove size, spacing, edge distance, all things that should be familiar to people familiar with the point 2 document, now in mandatory language format. When we move on to shear, chapter 8, a couple changes here that might be new. First of all, shear is bond critical, and I know there's some discussion about this, but in this document, shear is bond critical. And then we define the wrapping schemes that we permit for shear, so we can talk about a fully wrapped system, a U-wrapped system, or potentially a two-sided wrapped system. And a two-sided wrapped system might be something we see on a wall structure. Columns need to be completely wrapped. Shear design is again, as we should be familiar with, we have a concrete component, a steel component, and an FRP component. Shear is very much a displacement or a strain limited type of behavior, where if the strain exceeds a certain amount, we traditionally use 004, we start breaking down that B sub C component and it starts going away. So we limit our strains to 004. And we've done this in the point 13 document in one of two manners. So the one on the bottom on this slide that points to the call out on the right, we can calculate our effective strains in the FRP directly from a series of equations that have been presented in the point 2 document for a number of years. Or we can anchor our wraps using FRP anchors, and provided that we have a prescriptive design for the FRP anchors, and we meet this prescription. By meeting the anchorage design, we de facto meet the 004 strain limit on the FRP, and so it's the most efficient use of the FRP for shear. And so this is something that's new. It is now in the 440.223 document, and of course in the 13 document. Right now, this is the only application for FRP anchors, is anchoring shear reinforcement. Hopefully into the future that will also change. Design for axial. Axial is a little bit different. You're not typically looking to increase the strength of a column member or an axial load-bearing member, but more often it's ductility. Not necessarily, but that's more often the case. So we talk about fully wrapped systems. These are now contact critical. Bond to the concrete itself is not driving the behavior. The FRP is lapped around and bonding against itself, binding against itself, as it were. We still have limits associated with this: unconfined concrete strength. Before the application has to be less than 10,000 PSI. Flat surfaces, when we talk about rectangular columns, we limit those to the side dimensions of 36 inches and an aspect ratio of 2 at the moment. Circular columns, there's no particular limit. And limits to the effective strain on the FRP, similarly analogous, excuse me, to the shear limits or the debonding limits for shear and flexure, respectively. And typically when we're looking at axial, we're really looking at a combination of compression and bending, so a column that's also carrying flexure. And so we have the means of developing PM interaction diagrams for strengthened elements, and there I would point interested folks to the examples that are contained in the 440.2 document for generating PM interaction diagrams for repaired systems. I don't expect you to read this entire slide. The key takeaway is in red that the strength contribution of FRP systems during a fire event shall be neglected regardless of the use of fire protection. And so this has implications on what we can strengthen, and that the residual capacity of that existing element under the conditions of fire need to be respected. There is considerable discussion in 440.13 on fire. I think it's actually a little bit more even than in 562. And also we reference in this case, and I would encourage anybody interested in fire resistance, addressing fire resistance of strengthened concrete members, to obtain the TechNote 440.10, which really, I think, is remarkably clear in this issue and provides a couple of examples as well. The important thing when we're looking at FRP strengthening is that fire is an extreme limit state that needs to be considered very, very carefully. Finally, again and again, a slide I don't expect everybody to read. I think you've got the handouts and you can take a look at this. Inspection, testing, and evaluation, FRP materials, FRP installations are a little bit different than some engineers, some contractors are potentially used to working with. There are specifications for these, and we have a long list, and I would point out that the top of this list says the word non-exhaustive list of items that may be included in a field inspection program, and I've got A through M there. Also requirements for material testing, acceptance criteria, and a discussion of inspection of coatings. Coatings are not traditionally part of the FRP strengthening system, but they may be absolutely necessary to its performance, and therefore the inspection of coatings also needs to be addressed and is. So looking forward, and here's where the real opinions come in. 440S is a code committee, and therefore it's a sunset committee. We are being disbanded, I guess, sort of as we speak, and it will be reconstituted for the next code cycle. So what I'd like to do is give a couple of ideas here of some of the priorities going forward that we're going to pass on to the new committee. I don't know if they're going to take these up, but I think these are things that we are ready for. Absolutely the provision of seismic strengthening. This is covered to some extent in 440.2 in chapter 13. We would like to get a lot of that material into 440.13, and that way the document can also be cited directly from Code 369. And I believe our next speaker, Tarek, will be talking about seismic strengthening. So this is a really good segue for that. But so hopefully that will be in our next revision. I think provisions for masonry strengthening can largely be ported into this document. If you compare the 0.2 FRP repair of concrete to the 0.7 FRP repair of masonry documents, large swaths of the document are intentionally similar. Provisions for diaphragm strengthening, and this also speaks directly to seismic strengthening. There are two fairly significant international research projects presently ongoing. Both report regularly to ACI 440. And so hopefully we will have provisions for diaphragm strengthening in the next couple of years. Provisions for anchoring flexural reinforcement using potentially the FRP anchors and also URAP anchoring. And again, there's a fairly large working group and a number of studies currently ongoing that will hopefully address that. And I expect, although we presently don't have basalt included in the 440.13, I expect that basalt bars will certainly come into the next version. And there's a lot of minor issues that, given the time frame for producing 440.13, had to be tabled. And so we've got a long list of those that we'll be passing forward. I would be remiss if I just didn't make a quick mention about bridge structures. We keep in mind that 440.13 scope addresses building structures. There are guides for bridge strengthening put out by AASHTO, and I emphasize that all the AASHTO documents are presently guides. They are not written in mandatory language, but they do exist. And of course, if you're working with bridges, probably should be consulted. So with that, I don't know how we're doing on time because I didn't set my timer, but I think we're into questions.
Thank you, Kent. It was really a very good presentation with, you have compiled everything about 440S and the codes required and also the chapters. You addressed most of them. We have few questions, but as they came through the presentation, some you already answered, but I would still ask them. So the first question was, what are the key compliance considerations for engineers looking to adopt FRP systems as per the new ACI code?
Key compliant, not quite certain I understand the question. The specifications that are cited talk about the materials, they talk about their installation as well. So if we go to 440.12, for instance, that is an installation spec, and these are the requirements that we need to meet, whether it's surface conditions, surface prep, inspection requirements, and so on and so forth. So I think that is getting at the question, but maybe I didn't quite understand it. So maybe we go to another question, and whoever sent that could clarify a little bit.
Yeah, sure. Our next question is, how does ACI code 440.13 address safety concerns, particularly in the context of load-bearing structural elements?
It is a strengthening document. It is cited by 562, so we already have decided that we need to strengthen our structure. We have decided then that we are going to use FRP for portion of this, all of it, what have you. And so this is now the design code for implementing that. And as I mentioned, I think directly, we have in the 440.13 document at this point included the special load cases that need to be addressed with FRP. And then clearly all of the other applicable load cases coming from 562, which ultimately come from ASCE 7, when we're talking about buildings in the United States, need to be met. So as I said, the special load cases are presently included in 440.13, really in the interest of completeness.
Great. Our next question is, so it says, you did talk about fire and the reference documents. How about seismic? So I think this question might have come up before.
Yeah, I think we said there's a little bit of history involved. We did not have a full code cycle to produce 440.13. We actually did this in about 2 years. And I really need to give a nod to the committee. We had a very streamlined committee of 12 individuals who met at a minimum 4 times a year, not twice a year, and did a remarkable job in getting this document out in 2 years. One of the things, in order to get it out in 2 years, to match the 562 code cycle, because if we didn't get it out this time, it's not gonna see the light of day for another 5 or 6 years. We did table seismic in this version. Seismic only appeared in the 440.2 document under 10 years ago. The 2017 version was the first that had a seismic chapter. That was heavily revised in the 2023 version. And so I think that the number one priority for the next version of 13 is to integrate what we can of seismic including new material for diaphragms, for instance, into the 13 document. And that will be the job of the next chair of 440S, rather than me.
Yeah, we have other question. Can you explain why the unreinforced structure must have the capacity to carry 75% of the design live load?
So first of all, FRP materials can fail and can literally, in some cases, fall off a structure. That shouldn't happen. We might think about vandalism or something like that. And so the existing, and the problem is, of course, is that this may not be readily apparent. And therefore, the existing structure needs to maintain a certain residual capacity. Now, the actual numbers for that residual capacity, are sort of the wisdom of the industry. Those come from 562. Those come from, in some cases, ASCE 7. There's a lot of wisdom behind the actual factors that are selected, and we could probably argue about those all day long. But any external repair, and this is not unique to FRP, any external repair that has the potential of falling off or not being there at some point in the future, we need to address the residual capacity. Mm-hmm. Hopefully that answers the question.
Yeah, thank you. I think we don't have any more questions. So with this, thank you so much. It was a great insight, and we all will be looking ahead for the new code.
You and me both.
Yeah, sure. Thank you.
All right, thanks so much.